3 million. That is up to 3 million barrels of highly explosive crude oil sitting right beneath your feet. Imagine standing on top of a floating steel island holding all of that. It's the everyday reality of an FPSO. Storing that sheer volume of volatile fluid out in the middle of the ocean, it's an incredible engineering feat. But how do we actually pump it in, pump it out, and most importantly, keep the whole installation safe from a catastrophic structural failure or a massive explosion? Well, everything we're getting into today revolves around one absolute priority: disaster prevention. Welcome to The Explainer. Keeping these immense cargo tanks safe isn't just standard maritime operations. It's a highly specialized discipline that completely integrates cargo handling with advanced process engineering. We are going to look really closely at how modern FPSOs lock down their massive crude inventory securely. Okay, let's dive into our disaster prevention roadmap. We're covering hull stress and pumps, crude oil washing, slop tanks, and MARPOL compliance, and then our two ultimate defenses against explosion: flare systems and the inert gas system. First up, hull stress and pumps, preventing structural failure. We really have to address the first major threat to the FPSO. It actually isn't fire, and it's not a storm. It's the physical weight of the oil itself, which literally threatens to snap the ship's hull right in half if we don't manage it perfectly. You kind of have to think of the FSO hull like a massive steel beam, just like an I-beam holding up a skyscraper. As 3 million barrels of oil get loaded into different compartments, this beam takes on incredible bending moments. If you stack too much weight at the ends, the hull experiences sagging. The ends physically droop downward. Load too much in the middle, you get hogging, where the midship section bends upward. Exceeding those allowable limits causes fatal structural fatigue. That is exactly why the Marine Superintendent uses highly sophisticated cargo calculation software. It continuously monitors draft, trim, list, and hull stress to map out perfectly balanced loading sequences. And, to counteract those massive weight shifts, dedicated ballast pumps continuously adjust the ship's draft and trim. So, how do we actually move all that oil? Older conventional tankers used massive, highly confined, and incredibly hazardous pump rooms. Modern FPSOs, they eliminate them entirely. Instead, they use deep well submergible pumps. The pump itself sits directly inside the cargo tank, totally submerged at the bottom of the oil, while its motor sits safely up on the deck. And the really brilliant part of this design is the maintenance. Say a pump fails. You absolutely do not want to send a crew down into a toxic, highly explosive tank. With this setup, the entire pump assembly can just be unbolted and pulled straight up through a spool piece right on the deck. It completely removes the need for dangerous tank entry, all while maintaining high-capacity discharge rates to shuttle tankers. Next is crude oil washing, eliminating internal hazards. What happens when you pump that crude oil out? The tank doesn't magically stay clean. The crude leaves behind this thick, heavy, waxy sludge plastered all over the internal bulkheads. Leaving that sludge creates massive operational and safety hazards. So the crucial question is, how do we clean it? Well, international MARPOL regulations require a process called crude oil washing, or COW. Instead of washing the tanks with seawater, which, creates a massive pollution hazard, we ingeniously use the cargo itself. High-pressure jets spray warm crude oil from rotating nozzle machines inside the tank. This literally dissolves and flushes that waxy sludge right down to the floor. And it's all done simultaneously with the cargo discharge. The crude being offloaded is recirculated through the wash machines, then pumped straight over to the shuttle tanker. Crucially, because this high-pressure spray creates a highly flammable mist, the tank's oxygen level has to be kept strictly below 5% the whole time. Section 3, Slop Tanks and MARPOL, Preventing Environmental Catastrophe. There are times when we absolutely must use water to clean a tank, like before a structural inspection. But washing an oil tank with seawater creates a huge oil-water mixture, and we definitely cannot just dump that overboard. This oily water gets routed into dedicated spaces called slop tanks. The beauty of this system is its elegant simplicity. It relies almost entirely on gravity. The mixture enters a dirty slop tank, which is often heated to help break down the emulsion. Then gravity just does the work. The lighter oil floats to the top, where it's skimmed off and sent back to the cargo system. The heavier water settles at the bottom and is carefully decanted into a clean slop tank for final processing. But clean is a very strict, highly regulated term here. Before a single drop of that water is discharged into the ocean, it must pass through an oil content monitor. This automated system continuously samples the water.
If the oil content hits anything above 15 parts per million, which is the absolute legal limit set by MARPOL, the system triggers an alarm and automatically slams the discharge valves shut. Moving on to flare and vent systems, managing volatile gases. We've managed the liquid oil and the sludge, but now we have to escalate to the most immediate, volatile danger on board: highly pressurized hydrocarbon gases. The reality is, oil processing continuously generates excess gases, and pressure levels can spike without warning. To handle that threat, the FPSO relies on a robust flare and vent header arrangement. Think of these headers as massive, closed collection highways running the entire length of the ship. When an emergency shutdown triggers or a pressure relief valve pops, all that highly pressurized gas is instantly routed into these closed headers. They safely transport the gas away from the deck and directly into the flare scrubber. The flare scrubber's job is essentially to knock out any residual liquid droplets. This is vital because liquid hitting a flare tip is incredibly dangerous. Once scrubbed, the gas goes up the stack and gets ignited. Now, why burn it? Because safely converting toxic explosive hydrocarbons into CO2 and water vapor absolutely eliminates the catastrophic risk of an invisible, unignited gas cloud slowly accumulating and drifting across the deck. Now, over on the cargo storage side, everyday loading and discharging creates a really similar pressure problem. Pump oil in too fast? The tank could literally burst from overpressure. Pump it out too fast? It could collapse inward under a vacuum. Each tank has pressure vacuum valves to prevent this. But as a heavy-duty failsafe, we rely on liquid-filled PV breakers. If the main valves somehow fail, a severe pressure spike will physically blow the liquid seal right out of this breaker, instantly opening a massive unrestricted vent path to save the ship's structure. Finally, our last section, the inert gas system, the ultimate fire prevention. Venting alone just isn't enough. Even a completely empty, vented cargo tank is incredibly dangerous because the lingering hydrocarbon mist inside is just waiting for a single spark. We literally have to alter the atmosphere itself. Remember, to have a fire, you need 3 things: fuel, heat, and oxygen. We can't remove the fuel vapor, so we remove the oxygen. The inert gas system, or IGS, forcibly replaces the air in the cargo tanks with a scrubbed gas mixture, guaranteeing the oxygen level inside stays well below 5%. At under 5% oxygen, the tank atmosphere is chemically incapable of catching fire or explode. It just can't happen, no matter how much hydrocarbon vapor is in there. Let's actually trace this flow to see how it builds a complete defensive loop. The IGS burns heavy fuel oil in a dedicated boiler. That scrubbed flue gas, containing 14 to 16% CO2 and less than 5% oxygen, gets pushed through a scrubber tower that uses seawater to wash out soot and corrosive acids. But here is the really critical part. As the gas travels down to the cargo tanks, it passes through the deck water seal, right on the boundary between the safe area and the hazardous deck. This seal forces the gas to bubble through a column of water. If the blowers ever fail, that water barrier physically blocks highly explosive cargo vapors from flowing backwards into the IGS machinery. So, bringing it all together, you can really see how these 5 systems are deeply interconnected to prevent disaster. Deep well pumps safely manage the cargo weight to stop hull failure. Crude oil washing safely removes hazardous sludge. Gravity-fed slop tanks defend the ocean from pollution. The flare system neutralizes explosive gas pressure spikes. And the inert gas system actively kills the fire triangle by choking out the oxygen. We've thoroughly explored how the FPSO safely stores and exports its massive cargo. But where does all that pure, export-ready oil actually come from in the first place? In our next explainer, we are heading right into the very heart of the FPSO's topside production modules. When highly pressurized, chaotic fluid blasts up from the wellhead, how exactly do we separate the oil, the gas, and the water? I invite you to subscribe and join me, and we'll break down that incredible process next time.